Welcome back everyone. In the last lecture, we had seen the controllability canonical form of a uncontrollable system. We had decomposed the system into two parts, where one of the part was related to the uncontrollable state variables and the other was the controllable state variables. Today, we will look at state feedback control for uncontrollable systems. Remember, we had asked this question: if a system is uncontrollable, can't I find out a control law of the form u equal to minus kx such that we can change the eigenvalues of the state matrix to whichever point we desire? We will answer that today. So, again to recap, this was the way by which we had gone to the controllability canonical form of a system, where the first R vectors here we chose to be basis vectors of image of controllability matrix, okay, and this was what the transform system looked like. So, now what we will do is we will try to see if I introduce a control law of the form u equal to minus kx, what happens, okay, because we know that for the controllable case, when we used u equal to minus kx, we were able to change the eigenvalues of the system to such a way that we could get the desired response, right. So, now you see, if you have u equal to minus kx, x can be written as q into z, because I am using this transformation, and we will have minus k q z t, and k q I am calling as k hat, because this system itself we were using a hat notation, right. This we were calling a hat, this we were calling b hat, and this we were calling c hat, and d hat and d are the same. So, this is what the notation was. So, we are calling that the k matrix that we get for when we are writing it in terms of z variable, the control law, then we call that k hat. Now, remember this, if I partition this matrix, this is a R cross R matrix and this is n minus R, n minus R. So, in the same way, so basically what we can do, the z variable here, the first we can divide it into two parts. We have first R state variables and then we have the next n minus R state variables. The same thing we can do here also. Here we will take this as 1 cross R and this as 1 cross n minus R, and z is here z1 and z2 say. Okay. So, it is just a naming. I am partitioning k hat, I am just writing the first R columns of k hat as k1 hat and the next one as and k2 hat. Now, if I use this control law in this system, I can do that, right. I will use this control law in this system and see what happens. So, this was my transformed system. Now, I use the control law u equal to minus k hat z here, and notice that this is an R cross 1 matrix and this is a 1 cross R matrix. So, they can multiply out. So, once I do the multiplication, this is what I will get, and now I can take z common, this is what I get. And what is important here to note that this is an upper, again this is a upper block triangular matrix, and here the eigenvalues of this matrix will be the eigenvalues of this part and the eigenvalues of this part, right. So, the eigenvalues of a hat minus b hat k hat is nothing but the eigenvalues of this part and the eigenvalues of this part, and you can see from this expression that this part I can change with the help of k1 hat. The eigenvalues of this part can be changed with the help of k1 hat, because that is in our hand, whereas the eigenvalues of the AUN part I will not be able to change, right, and that is the reason. What was AUN? AUN were your uncontrollable eigenvalues. So, the uncontrollable eigenvalues of a system cannot be changed with state feedback matrix, state feedback control law. The uncontrollable eigenvalues of a system cannot be changed with state feedback control law, whereas the controllable eigenvalues of a system can be changed with state feedback control law. That is the reason we were actually calling these eigenvalues as controllable eigenvalues, because I can control these eigenvalues, I can change these eigenvalues with a state feedback control law, but these we were calling uncontrollable eigenvalues because I cannot change these feedback these eigenvalues. Okay. So, now let us look at examples and see how to construct state feedback for a uncontrollable system. So, this was a system that we had taken earlier. So, for this system let us try to see what will be the state feedback. First, the transformed system will look something like this. Again, the procedure you already know. Now, suppose I ask the question, change the eigenvalues of the system to -2, -2 and -2. So, again remember the eigenvalues of this system and this system are the same because they are related by this transformation, a similarity transform. Okay. So, the eigenvalues of this and this are same, remember that. Now, I want to introduce a control law of the form minus kx. Again, I can, instead of writing it as minus kx, I can also write it as k hat z, because once I know k hat I can get the actual k. So, I have to come up with a k hat such that I can change the eigenvalues of this system. Now, what are the eigenvalues, present eigenvalues? Since I am already in the block form, I can directly read out the eigenvalues. Here one of the eigenvalues -2 for the original system and the other eigenvalue. This block, since this is lower triangular, the diagonal elements itself are the eigenvalues. So, the eigenvalues of this system are -2, -4 and -6. Just by looking at this matrix I can tell, because see this part will, this union, the eigenvalues of this will be the eigenvalue of the state matrix. Now, the eigenvalue of this part is -2 and this part you can see is a lower triangular matrix. A upper triangular or a lower triangular or a diagonal matrix has eigenvalues as the diagonal elements. So, here -4 and -6 are the diagonal elements. So, the eigenvalues of this matrix are -4, -6 and -2, but importantly -4 and -6 are the uncontrollable eigenvalues. And since -4 and -6 are uncontrollable eigenvalues, there is no way that I would be able to change all the eigenvalues to -2, -2, -2, because these cannot be changed. Okay. So, that means this here in this example at least we know that we will not be able to place the eigenvalues of the system at -2, -2, -2. Let us take another example where we say that same example remains the same. Now, we are saying that change the eigenvalues of the system to -20, -4, -6. Now, this is doable because -4 and -6 I am not changing. Only thing that I have to do is I have to change -2 to -20 and we will see how to do that. So, the first step is that you see, since I have already block apart triangularized it, it is already in the controllability canonical form, I can just look at this part which is AC and this part which is B1. I can take this smaller system AC and B1 and place eigenvalues for AC and B1 using B1. Okay. So, place eigenvalues of AC and B1, where do I want to place? I want to change the eigenvalue from -2 to -20. Okay. So, we will use the Ackermann's formula. Remember the Ackermann's formula, this was the Ackermann's formula, we will use that. Okay. You can go ahead and use the other ways also, the controller canonical form, you can use the controller canonical form also to place the poles. I am directly using the Ackermann's formula here for ease. Okay. So, first of all, what is the desired eigenvalue? So, the desired eigenvalue is -20. So, the desired characteristic polynomial is s plus 20. So, now I have to find this. So, I will plug in place of s AC. So, this is what I get 18. So, and then what is the controllability matrix here? Controllability matrix is B1, AC B1 and all, but since this is just 1 cross 1, I will just get this controllability matrix is B1, and so finally the k hat matrix, once you use this formula which is 1 into C this inverse. So, 1 inverse multiplied by this will be 18. So, this is what the formula says. So, k1 hat will come out to be 18. So, once you have k1 hat, you see, remember one thing, what is our control law like? Our control law is this, right, in terms of z. So, this is a 1 cross 3 matrix. What we have found is a 1 cross 1 matrix. So, we have basically found out one element and we have to again add something so that it becomes a 1 cross 3 matrix. So, we will see how to write that now. So, the control law will be of this form. Remember, u is equal to minus kx. So, the first element will be 18 here and the other two I do not know what that would be. Okay. As a matter of fact, I can choose anything because that part is not going to influence. Okay. Why cannot that part influence? Notice again, why cannot this part influence anything? Because you see, if I take this system and if I write down, let me write it down here. So, AC A bar 0 AUN here. So, what will be the so this will be ZT, what will be this part? B1 0, U is becoming 18, K2 hat, K3 hat, right. So, B1 was anyways 100, right. So, what will this become? So, if you multiply this out, what do we get? We get AC minus 18, okay, ZT is here. So, ZT is here. So, we get AC minus 18, then we will have here A bar minus, so we will have 18 and then we will have A bar minus K2 hat, K3 hat here and then we will have 0 here, 0 0 and there we will have 0 0 0 0, this not 0 0 0 0 AUN, we will have AUN and you can see that K2 K3 hat does not show up in these terms. So, whatever I choose K2 hat and K3 hat, they are not going to influence the eigenvalues of the new system. New system as in the system we get after we have used the state feedback. So, I can choose K2 hat and K3 hat to be anything. So, I am choosing it to be 0 0, you can go ahead and choose something else also. So, this becomes your u equal to minus k hat z and now after, since this is in z, so I have to convert it to x because the actual system is in x. So, I will use the transformation here. So, z will be replaced by q inverse of x. This is what I get. Once you do the calculation, this will it turns out to be, it comes out to be the same. So, this will be the K matrix that you have. If I show you now, notice that this is the A matrix, this is the B matrix and now this is the K matrix 18 0 0. Now, if I do A eigenvalue of A minus Bk, because you see the control law that I am using is Ax plus B minus of Kx, where this is your K and this is your x. So, therefore, the final matrix becomes A minus Bkx. So, therefore, these are your eigenvalues. Yeah. So, these are your eigenvalues here. Okay, and you can see I have placed it at minus 20, minus 4 and minus 6. Let me take another example where the controllable dimension of the controllable space is a bit bigger. So, this is their system. You can go ahead and find out the controllability canonical form in this way. So, this is the controllability canonical form. Now, the eigenvalues of this system are, where are the eigenvalues of the system? 2, 4 and minus 6. Now, in this case the control AC is 2 cross 2. Okay, and AUN is 1 cross 1, minus 6 is the uncontrollable eigenvalue, and if you find out the eigenvalue for this part, it will come out to be 2 and 4. And I want to change the eigenvalues of this system to minus 2, minus 4, minus 6. Now, this is doable because minus 6 is an uncontrollable eigenvalue, this I can anyways cannot change. 2 and 4 I can change to minus 2 and minus 4, and that is what I am going to do. Again, I will use the same ideas that I had shown you just now. So, what is the desired characteristic polynomial here? I am just concentrating on this part, and this part is this is my AC and this is my B1. I am just concentrating on the smaller system now, AC and B1. Now, for this smaller system, you see where is the desired what is the desired characteristic polynomial? S plus 2 into S plus 4. Now, x desired AC I have to find out. So, this is what it would be, you multiply it out, this is your x desired AC. Now, what is the controllability matrix? The controllability matrix is B1 AC B1, this is what you get, and once you have that, you use the formula that is given here. Using that formula, you will get to be this to be the solution. Remember, this formula was for the n equal to 3 case, right. So, if you have more than if you have n equal to 2 case, then this will get replaced by 0 1 here. Now, once you have K1 hat, now we can write down the control law. So, you see k1 hat comes out to be this, which means your control law u equal to minus k hat z. So, this is the term that is coming, and then this part I can choose anything, like I told in the previous example. I am choosing it to be 0, you can choose it something else also, does not matter. And then once you have done that using the transformation here, so this k hat, k will be coming out to be k hat q inverse. Once you do that, this is the expression that you get. So, if I go ahead and do this simulation, you will see that this was my A, this was my B, and the k hat was 12720, k comes out to be k hat into inverse of q, q is already defined. So, this is my k, this is the k expression, and then A minus B k will come out to be this, and the eigenvalues are at -2, -4 and -6. Okay. So, this actually gives you an idea as to how we can find out the state feedback controller for uncontrollable systems. If we want to change the eigenvalues which are uncontrollable, we will not be able to do that. However, if we want to change the eigenvalues which are controllable, we will be able to achieve that. Okay. And you can also see that when I am designing this controller, that part, there is a part which we can choose arbitrarily. So, I can actually go ahead and find out infinitely many controllers. Okay. So, among those controllers, some of the controllers may be good, some of them may be bad. So, what is the good and bad? Maybe I will talk about that sometimes if possible, but in general you understand now how to design state feedback controllers. Now, think of a situation, just think of a situation now. Suppose you have a system which turned out to be an uncontrollable system. Now, since it is an uncontrollable system, you already know that some of the eigenvalues you will not be able to change. And it turns out that the eigenvalue that you will not be able to change is on the right half of the complex plane. What will happen? So, for example, in this example, the eigenvalue that we wanted to change was 2 and 4, but they were the controllable eigenvalues. The -6, this eigenvalue was uncontrollable, but this is on the left half of the complex plane. Suppose instead of that, suppose it was in the right half of the complex plane. Suppose this came out to be +6. Okay. Then what will happen? See, in that case, you will not be able to design any state feedback controller that is going to change the location of those eigenvalues, right. Now, if you cannot change those eigenvalues, now think of the solution of the state equation. The solution of the state equation will have a term like e to the power of 60. In this case, of course, it is -60, but suppose the eigenvalue was 6. In that case, you will get e to the power of 60 or e to the power of 80, where a is a positive number. Which means that particular state, this is a transformed state, of course, because we are in the controllability canonical form. So, this state will blow up as t tends to infinity, right, and that means this state will create a problem, because internally this state is blowing up and the system will become unstable. It might turn out that you will not be able to see this in the output, but inside the variables itself will keep on blowing up. But at some time, you will at some point of time, practically the system will damage basically. Okay. Why do I say you will not be able to see at the output? Because you see why, when we found out the transfer function in the last class at the end of the lecture, when we found out the transfer function, the uncontrollable eigenvalues never showed up in the transfer function. Right. Now, if the uncontrollable eigenvalues are never showing up in the transfer function, and suppose I ask you, I give you the transfer function, the uncontrollable eigenvalues never showed up in the transfer function, right. Now, if I ask you, suppose if I give you a step input, what will be the output of the system? Then you will just use the transfer function and find out the output of the system. But the uncontrollable eigenvalues never showed in the transfer function. So, at the output you will never be able to see the effect of the uncontrollable eigenvalue, right. But since in the state equations we can actually go ahead and see the internal this uncontrollable eigenvalues also, you can see that the states are blowing up, although at the output we are not seeing that. So, which means internally maybe one variable is blowing out. So, after some time the system might burn out or something. Okay. So, that is the reason this internal view of this state space view actually gives you more understanding about the system, because only just by looking at the output you might not know how the system is behaving, because internally there might be some variable which keeps on blowing up. Okay, this variable is getting captured in the state space modeling. Okay, and which might not be true, which you might not be able to figure out when you just look at the transfer function of the system. Now coming back to the point, suppose the uncontrollable eigenvalue is on the right half plane, that means you won't be able to change this, right? So which means that there is no way that you will be able to stabilize the system. Okay, now suppose the uncontrollable eigenvalues are all on the left half plane. Okay, and for example this was the example, right? In this example the uncontrollable eigenvalues in the left half plane, however the controllable eigenvalues are on the right half plane. Now if I would have found out the solution of this state equation, I would get terms like e to the power of 2t, e to the power of 4t and e to the power of minus 6t, right, because these are the eigenvalues of the system. Now these terms will blow up as t tending to infinity. So as a control engineer, my work would be that I have to come up with a controller such that these eigenvalues gets changed, and that is what I did in this example. In this example I changed 2 and 4 to minus 2 and minus 4. So when I use this control law u equal to minus kx, when I use this control law, the new system that I got, this was the new system, right? In this system eigenvalues are at minus 2, minus 6 and minus 4, which means when you solve this you will get only terms like e to the power minus 2t, e to the power minus 6t and e to the power minus 4t, which are all dying down to 0 as t tend to infinity. So I have been able to stabilize this system. Okay, and this is what is known as stabilizability of a system. So when can we stabilize a system? Okay, when can we make a system stable? The meaning of that, this statement is that. So when can we make a system stable? We can stabilize a system if the uncontrollable eigenvalues of the system are all in C minus. Because the uncontrollable eigenvalues are already in C minus, I do not have to think about stability of that. I cannot change that but by default they are already in the left half of the complex plane. So it is, I do not even have to think about those uncontrollable eigenvalues because they are stable. Okay, the only ones which I have to think about are the controllable ones. If the controllable ones are not in the left half, I will just change them to be on the left half using state feedback controller. So that is why a system is said to be stabilizable. I can stabilize a system if the uncontrollable eigenvalues are in C minus. I hope you have got some idea as to what this uncontrollability is, what is controllability, how do we get to state feedback. I hope you have got some idea. We will take up with the two other questions that we had asked when we started the lecture. In the previous lecture we asked three questions, right? So one of the questions I was answering, I have answered that today. Okay, I have completed that answer in the last two lectures, that how do we find out state feedback controllers for uncontrollable systems. The next two question remains is that what happens if we do not have the state variables. Okay, we will have to answer that question as we go along and we will do that soon. See you in the next lecture. Thank you.